Hello and welcome to this tutorial. Today we'll be walking through a large model and practicing just how to look at FEBio models and what we can do with them. I've chosen to open it in FEBio Studio. We also could have opened this in a text editor to look at this .feb file, but let's take a look. So if I rotate the view, we see we have 9 bones. And they're all different colors, and there's kind of a lot going on. So we'll break it down into steps. I'm going to drag this down so we get a better view. And I'm also going to exit out of the build panel because we won't be building anything. We'll just be looking at something right now. Everything we have is already built. So now that we have a clearer view, we can work our way through the model viewer. So in geometry, we have different objects, 143 parts, over 1,000 surfaces, lots of edges, lots of nodes, and lots of these, 40 of them are named. One thing that might be the most useful thing we can do with this is basically looking on here. These are our active parts. If we click this button, then it will highlight them as we select them. So you can see different parts. We won't interact with that a lot, but sometimes it's helpful when we're working with a mesh or with materials and things like that. Let's move on to the model itself. So if we go to materials, this is very big. A very important part of what we do. So we have a rigid body, C7 through T1. So this is the base, and it is totally rigid. There will be zero deformation in this bone structure. And notice there are 2 bones, C7 and then T1 is on the bottom, and they are defined to be part of the same material. And this material is a rigid body, which means there is zero deformation. And so that means there will be zero deformation between them as well. They are locked in place relative to each other. And just to go back to objects, we could find what part they are. So this is multiple parts that are defined as the same material definition. And actually that's listed right here, part 6 and part 12. So there's part 12 on the bottom, and here is part 6. So it's still being highlighted, and I don't want that. So I'm gonna deselect this button. Okay, so C0 is a rigid body. This is the occiput or base of the skull. Your brainstem kind of goes right here, and it turns into your spinal cord right in this opening. Then we can go through this cortical and trabecular. We can see their little triangle, little yellow alert, warning symbols right here. And that means, well, in this case, we can look at this, we can click right here, and it will give all of our warnings. And so if we scroll down, oh, actually, it's just right here, cortical and trabecular. So these two, the materials aren't assigned to anything. And that's fine. It's not hurting anything for them to be there, but they're also unnecessary, just kind of vestiges of things that people have done in the past, and I haven't seen a reason to take them out yet. This FC represents the facet cartilage. So rather than using this, I'm going to highlight by highlighting these and then clicking this arrow. And so we can see the facet cartilage is on both sides and at every joint level. The TM stands for the transverse membrane up here at the top. The TL is the transverse ligament. And so those work in tandem to hold the base of the skull and the rest of the cervical spine all together. So they kind of act as a connecting point between all of them and hold it to this. You can see this kind of round structure right here. This is called the odontoid or dens, the odontoid peg also. And that is what your skull spins around. A very large percentage of your axial rotation motion comes from right there. So shaking your head no. A lot of that comes from right there. So the nucleus, all of these are part of one part definition, and they make up the very center of our intervertebral discs. Now, all of these, 154, these are named based on how we previously had the model set up with their fibers, but now they are defined to simply be, if I highlight the entire annulus fibrosus, or the outer part of an intervertebral disc. So this one makes up C2-3 intervertebral disc. This one makes up the next one, etc., all the way down. So this is that one down there. And then the rest of these are just kind of left in here as vestiges. They aren't assigned to anything. Now we get to the bones, the rigid bodies. C1 is up here, part 132, and then all the way down to C6. And then we also have the trabecular bone. The trabecular bone is on the inside, and the cortical bone is on the outside. This C1 shows the outside or cortical part of the bone, and this shows the trabecular bone on the inside. You can see how it highlighted differently there. Okay, and that's all our materials. Our bones are rigid, and our facet cartilage and our intervertebral discs are defined more softly. And so actually, let's talk about that. If we get into the mechanics of it, the nucleus in the middle of all the discs, I'll highlight that again. This is represented pretty simply as a Hookean material, which is very basic linear material properties with a Poisson's ratio of 0.49, which is essentially incompressible. And if we come to these, the annuli fibrosi, which is the technical plural for annulus fibrosus, but it just sounds weird also. If we highlight this again, remember this is the outside, makes up the rings that form the outside of the intervertebral disc. And so this is made up of a very special material definition. So it is a solid mixture. What does that mean? The solid mixture just means we take multiple material definitions and combine them into one. So what are our material definitions? Solid 1 is a Holmes-Mao definition, which there's more information on that on FEBio. Basically, it's a hyperelastic material and nonlinear, which represents the intervertebral discs pretty well. A linear material definition is really good for metals and ceramic and things like that, but our biological materials are pretty complicated comparatively. Our second material is a fiber exponential power definition, which represents fibers. There's a lot of studies and math that went into creating a good fiber definition, and this represents the fibers which are in your annuli fibrosi that kind of hold it all together. There's a second definition as well, which is the same thing, but representing the fibers that go in the other direction. So you have two fiber families, one that goes at kind of a 30 degrees from the horizontal, and another that goes negative 30 degrees from horizontal. I don't know if I got plus or minus right there, but you get the idea. And that is what these definitions get into. So theta, phi, that gets into that angle. And then this cylindrical definition um, says that they change with respect to a specific axis. And so this center defines the center of that axis, and this axis vector defines which direction it points. If I come up here to view and turn on, where is it? Show fibers right here. If I show fibers, then this fiber viz tool pops up. And we can see that there are these little green and red lines that show up that represent the fiber families. And we can see that they typically produce this kind of X. And so that represents the one fiber family coming this way and the second fiber family coming this way. We can change, the way we look at this. Scale factor changes how long they are. Maybe right there is kind of nice for how we are looking at it right now. We can see that the cylindrical definition means that even when we look from this angle, when we look dead on, again, they are X shaped. So that X kind of wraps around the material. All right, so that's that. I also would like to talk about the TM and TL. These were defined using surfaces rather than bodies. So they are a surface definition that is assigned a thickness, and we can see more about that in the object. So part 5 is a shell object. All it has is, and part 9 and part 13 are all shell objects. And so what that means is they defined faces that make up a certain shape and not volumes. So these have triangular elements that are then assigned a thickness mathematically, but they are not represented as actual volumetric shapes that have depth. They are essentially two-dimensional. With that, I think we can move on from our materials. We can move on to boundary conditions. So COTL, COTM, C2TL, C2TM, and then also C1TL, C1TL. Left side, right, and right side. So what this is this connects the TM and the TL to their respective rigid bodies. So this defines a certain number of elements on the side here and says, okay, they are rigidly connected to this material, in this case, C0. And then this one connects TM, the transverse membrane, to C0. And then those are redefined in the different attachment points. So that's everything for boundary conditions, and we can move on to loads. So we have two pressure loads, and they both start in the initial step, which means they go on the whole time. And they have load curves as well that control how they ramp up. So load controller 1 and load controller 2 control both of these. So let's go into our curve editor and we'll look at loads, pressure load 1, we'll look at the pressure. So they ramp up from 0 to 1 over the course of 1 second. Pressure load 2 does the same thing. From 0 to 1 second, it goes from 0 to 1 times the pressure. And the pressure value is 0.1 for pressure load 2 and negative 0.1 for pressure load 1, and these are assigned to different selections in here. So pressure load 1, which is the negative value, is assigned to the tops and bottoms of the intervertebral discs. Pressure load 2, which is the positive one, is assigned to the outer ring between the nucleus pulposus and the annulus fibrosus. And so that pushes out and pushes in, mimicking the load applied by the weight of the head, for example. And so this is how we pre-tension our intervertebral discs so that we get a very realistic response out of our models. So that's that. We can go into contact now. These models have a lot of contact, and that's because each one of these facet joints needs a contact definition between them. So we can see C01 LFC. So that's C0 to C1 on the left side, facet cartilage. So this one defines this. We can see our primary surface. And if we select this, we'll see the bottom. And then our secondary surface is the top. And so what this does is this mathematically says, all right, if these two surfaces bump into each other, normally the computer wouldn't do anything about it. But since we have a contact definition set up, then if they start to go through each other, then it will push back and will say, never mind, I'm adding a force to push these two surfaces back apart. Enforcement method, augmented Lagrangian, is like the penalty method, which we also could have chosen, but it adds some Lagrangian multipliers, which we can get into it later. Basically, is a little bit more math heavy for the computer, but does a better job enforcing the contact. This penalty value is very important because the augmented Lagrangian is built off of the penalty method, and the penalty method applies this multiplication factor times how much the two surfaces have penetrated. There's more than that, but that's basically the idea. And so with augmented Lagrangian being built off of that, this penalty factor does a lot. If you change this to 20, then that's twice as strong as a value of 10 that it's going to do. And 10 is already pretty high. Most times, anywhere from 1 to 2 is good, especially with this auto penalty checked. Only in these models, because they are so complicated and these shapes are so hard for the computer to manage, do we need a penalty factor this high? And that comes after a lot of trial and error. Other important factors are this search radius. That is how far it's going to search for the other surface. It's going to start at the 1, and it's going to say, okay, from this node, do I see the other surface within this distance? And this is how we control that distance, is this search radius. And so changing this will change a lot, because if you have it too high, then it will come in and maybe from this distance will start to pick up, oh, the other surface is here, we need to start doing something, when you shouldn't. But if it's too low, then maybe it will go right on through and it won't be able to find the other surface. So playing with the search radius is also very important if you're having issues there. These max aug and min aug, 20 is good. If you want the augmented Lagrangian to really kick in, if you feel like it isn't doing enough, then you can turn this min aug maybe just up to 1 to get it started. But most of the time, you can just leave it at 0. And if it's needed, then it will start to do that. So we have a lot of contact interfaces with the facet cartilage, and they're all essentially the same. They all have slightly different parameter setup, just because that's what has worked best after a lot of trial and error. And then the TLTM and C2TL, that defines the sliding interface between the odontoid peg right here and the TL and TM. And I've never had any issues with them. Basically, the OGLAG penalty 1 auto penalty has always worked well for me with that. Moving on to rigid definitions. So we have rigid fixed, and here we can see that the rigid material selected is this C7T1 material. So this complex down here is totally rigid and not allowed to move at all because of this rigid fixed definition. It is fixed in place, and it is fixed in place in all 6 degrees of freedom. So X, Y, Z, and rotation, all 3 are all checked, so it's not moving anywhere. We have another fixed definition for the trabecular bone inside C7. So again, just that inner portion that is not going to move at all either, all 6 degrees of freedom. And then here we have a rigid fixed applied to C0, so here at the very top. However, we can see that we only have 2 of the boxes checked. So it is allowed to move in X, Y, and Z as much as it wants, and rotate around X as much as it wants, but it's not allowed to rotate in Y or Z. So the C0 is not allowed to spin in the Z direction, nor in the Y direction. So in this case, it's not allowed to shake its head no or tilt, but it is allowed to rotate around the X axis. So it is allowed to shake its head yes. Now we get to our last rigid constraint, which is rigid rotation. And here we can see that it is also applied to C0. So here we're forcing it to rotate in the RU, which is another way of saying it's rotating around the x-axis. So that one that we left free, now we're forcing it to rotate in that direction. And so our U is around the x, our V is about y, and our W is about z. So I'm going to leave it there. And this is the value in radians that it's rotating. So it's going to rotate negative 0.73 radians. So it's going to tilt back and extend 0.73 radians. And there's a load curve associated with this. Look at it. If we come to rigid boundary conditions, rigid constraint value, there we go, which corresponds here. We can see that this one actually starts not at 0 seconds, but it starts at 1 second and goes to 2 and ramps up from 0 to 1. Why is that? It's so that the other, if you remember the pressure loads, we want those to ramp up from 0 to 1, and then that's when we start the actual rotation of the model. So we give it a sec to get its pressure right, and then we do our actual test on it. So that's why we break it up into essentially 2 steps. All right, there's that. Discrete. So we have 40 discrete definitions, and that defines the spring elements that make up different ligaments. So flaval, between different joints. You can look up what all of these are. Their abbreviations are pretty straightforward once you know what they are. Steps. We have our initial step and our step 1. This is a very important thing to be aware of. So we have static analysis. It's all quasi-static. We're moving slowly. And we have 2,000 time steps of 0.001. So it's going to run for 2 seconds. We could have broken this into 2 steps and had initial, then step 1, then step 2. But in this case, we simply used our load curves to do the same thing. So it'll run for 2 seconds. We have our auto time stepper values. We have optimal iteration set at 500, which is very high. Our minimum step size is 0.001, which is actually our nominal step size. So the auto time stepper will step forward at 0.001 time increments. And if it recognizes that, wow, that was really easy to solve, then it will actually increase the time step up to our max step size, which we define as 0.1. So just from experience, what I've seen with this is it will initialize and then take the first step. And then for that first second, right, as it's just ramping up the pressure, it will take pretty big time steps. And that's what we want. We don't want these output files to include information from all those tiny little steps because it has to save all the information of the whole model at each of those time steps. We like to have our step size increase to reduce that file size. And then once it starts to struggle, which happens pretty quick, once the once the rotation starts, that's when it starts to go back down in time step size. And this cutback and aggressiveness define how quickly it will cut back once it starts to struggle. Here are our load controllers. We can see that basically we have 1, 2, and 3 that are active, but all of these with the warnings are actually very important. Many of them are very important because they actually define the properties of the spring elements. So we don't want to delete these because that will alter how the spring elements work. All right, and then from there, we do have some things added to our output. You can right click on the plot file. So plot file, like our xplot file, which is our output. And so we can change the output parameters. We can say edit output, and there are all these different options for what we might want to include. And for our purposes here, this list is what we need. You can also do the same for the log file. That's the model, and we can go ahead and run. So I'm going to hit FEBio, save, that's all good. And it's going to give warnings because a lot of these material definitions aren't assigned any parts. We can just continue. So we can see it started to run. You can see our log output, and it is solving. So you can see it started. Oh, there's our warnings. We can see it started at 0.001 time step like we defined. Anyways, this is going to take 15 minutes probably. Yeah, it's 1%. So I'm going to bring in the xplot file so we can just look at it. Okay, here it is. So these are the results. It's still running, so I'm going to leave that there. I'm going to exit out of notes so we can see the timeline better. Move this over. So like I said, we can see that it gradually began to take larger and larger time steps up to almost 0.1 in size. And if we notice, nothing is really happening up here. That's just as the intervertebral discs are gradually pressurizing. And then after 1 second, oh, it started to move a little bit. And so we can click through here. I'm using my arrow keys to click through the results, and it gradually works its way back. We can see right here, there's a little cluster of time steps because it had an issue. It struggled to work its way through, so it cut back the time step. And then after that, it came back to larger time steps because it worked its way through the issue. So we can see it made it all the way to the end and looks pretty good. There are a lot of things we can look at with this, but rather than do that, what I want to show you is what I've been doing with this. So I'm going to bring in another FEB file that is based on this model, but slightly modified. And since we already have the results of the FEB file and it's kind of slowing down my computer, I'm actually going to come to FEBio and hit stop FEBio so that it doesn't worry about that anymore. So I'm not going to open results because we already have that. So I'll just close. All right, so this is the same FEB file with a slightly different name because there's a slight change to it. If you'll notice, C0, C1, and C2 are all the same color. That's because they're all the same material definition. They're all part of C0. Simply by reassigning the parts to this other rigid body, we have essentially simulated a fusion. By evaluating the differences in results between this model and the previous model, one that's unfused, that's how we're able to look at the different outcomes from fusing this part of the spine. And so with that, I want to thank you so much and wish you a great day.